Let's take a look here at the properties of leaving groups. We're going to look at that, and then we'll dive into what nucleophiles are and how to distinguish if they're good nucleophiles. Remember that leaving groups, when they leave, they take a pair of electrons with it. So if you think back to acid-base chemistry, the factors that stabilize electron density will make better leaving groups. This is true, remember, if you think back to the factors that stabilized conjugate bases, right? So a strong acid is strong because its conjugate base is stable. Some of those factors that make those conjugate bases stable were things such as polarizability, right, resonance, so on and so forth, right? We talked about a lot of those in one of our previous lectures. So in general, by the way, weak bases will generally make better leaving groups. Now, little review as to how we look at the strength of an acid. Remember, we talked about pKa's. So a smaller pKa means that we have a stronger acid. A stronger acid results in a weaker conjugate base. Right? So if we look down here below, let's just summarize here. Of course, there's more than this, but these are the general ones that you're going to see. Halogen ions. They're among some of the weakest bases. And if you look at pKa's, so if we look at HI, the pKa of HI is -10. It's one of our strongest acids. And therefore, its conjugate base is one of the most stable conjugate bases. It's one of the weakest conjugate bases. So it's a stable ion. It's large, it's polarizable. Remember, we talked about that before. So HBr comes next. This has a pKa of -8. So it's slightly stronger of a base, still a very weak base though. You go down to hydrochloric acid, that's -7. And then HF pops up all the way over here at +3. So we typically would see iodide, bromide, and chloride here as leaving groups, not so much fluoride here. There are some other important leaving groups for us. Water is one of them. So whenever we can lose H2O, it's a great leaving group, right? And alcohols too. Notice that when they leave as leaving groups, they're uncharged, and that's nice. So there's no negative charge to try to accommodate. We just already are neutral. Now those are our basic good leaving groups. We'll talk about more as we progress through this semester, but this is good for this chapter. Now, what about bad leaving groups? So there's some things that are just bad that we're not going to kick off. And these are bad leaving groups, and specifically we're looking at things like substitution type reactions, right? So we do see, for example, hydroxide as a leaving group in second semester, but it's not part of an SN2 type of a reaction. But hydroxide is not a good leaving group. It's a bad leaving group for substitution. And that's again because it has a pKa. It comes from water, right? So water is the acid that gives you hydroxide. And H2O has a pK of 15.7. So that's a, we know from general chemistry, hydroxide is basically a strong base. Hydride, it's another one that we're not going to kick off. So we don't really have H- getting kicked off of molecules and floating around in solution, for example. This has a pKa of 35 from H2, right? So that's between 15 and 35, that's a difference of about 20. So H- is about 10 to the 20 times more basic. And then we go way over to the other side here with a carb anion. So this is CH3-, it comes from CH4, and that has a pK of 50. It is basically the strongest base that we're going to see in organic chem. Now, there's a little trend here, and if we look at this little table, we can put this, we can kind of categorize leaving group, ability based on pKa's. This is rough though, guys. So when we look at this, between -10 and about 0, we might classify those as being good leaving groups. All right, and at the other end of the spectrum, right, we'll say from about 11 up to way up to 50, those are typically going to be bad leaving groups. Right now, right there in the middle here, 0 to about 11, these are what we might classify as being moderate. And we tend to, at least in introductory organic chemistry, we tend to kind of hang out in the green area or the red area. And we don't dive in very commonly without some help into the moderate region. Of course, that depends on who's teaching the class and what they want to emphasize, but that's the general trend that we see there. So I want to talk briefly about this distinction between nucleophiles and bases. All right, so if we look at this first reaction up here at the top, here's a B minus, right? So that B minus, that's your base. Notice it's coming over here and grabbing an H. Okay, so if that species makes a bond with a proton, right, in other words, the B, it's acting as a base. Easy thing to remember, right? Now, if the species, and the species we're talking about is this guy here, if that makes a bond with a carbon, it's acting as a nucleophile. And that's how we can determine whether or not we're dealing with a base or a nucleophile.